I'm hoping all's good. All right, I'm going to go ahead and start. And yeah, interrupt me and let me know if things are not working right. If you have questions, put them in the Q&A, and I will switch back and forth. So I have to switch to the tab with my presentation on it to scroll it through, and I'll try to remember to switch back and forth to check on the Q&A there. All right, so here we go. Today I'm going to talk about cryptography, past, present, and future. And I have far more slides than I can possibly do in the time we have. So let's see, what could I do? I could go super fast and you won't follow me, and then I'll put you all to sleep, or we'll just do some subset. So I guess we'll do some subset. So basic terms, cryptography is when you encrypt or decrypt a message with a key. Cryptanalysis is trying to decrypt a message without the key. And steganography is just a term for hiding a message. A number of ways one can do that, like hiding them in images or other places. The plain text is the message in readable form. The ciphertext is the encrypted version of the message. And of course, the key is a shared secret between the sender and the receiver, used for encryption and decryption. We use Alice as the sender and Bob as the receiver. Those are the good guys. And then we have Eve, the evil eavesdropper. And here's a diagram of how that all fits together. All right. So, okay, I'll pop over, see if there's any questions yet. And I see nothing. All right, moving along. All right, how do we use cryptography? Well, it's used in lots of situations. War is obviously one. Cell phones can use it to encrypt information to transmit. Obviously, bank transactions are encrypted, secure web connections, James Bond and spy stuff. Storing passwords online is done with encryption. Digital signatures, just privacy in general. One of the oldest crypto systems known is Caesar Cipher, and the idea there was just to add 3 to each letter with wraparound. And of course, this was used in ancient Rome for various types of messages, mostly related to wartime with Caesar's legions and the Roman war machine. And here's an example. So if my message is meet me for coffee, you can take each letter and add 3 to it, as it were. And then here's the ciphertext. So M, you add 3 M, N, O, P, right? Then E, F, G, H, right? And so forth. So there's the ciphertext, P, H, H, W, P, and so forth. And then to decrypt it, you would just subtract 3. Right, or you can add 23 with wraparound, right? It's kind of like clock addition. If you add 2 hours to 11 o'clock, you get 1 o'clock, and the same works with letters with the alphabet here in encryption. So, all right, so there's a challenge handout, a PDF, I think, that was attached to the event, hopefully. And here's a couple of, I believe these are Caesar Cipher encryption, so you can try those on your own. And I helpfully supplied an alphabet for you. That's sometimes helpful to remember the alphabet, so you can easily add and subtract 3. All right, moving along. So my superpower is putting people to sleep with my voice, and that seems to work really well. And no, we are not going to do that now. Okay, sorry about that. All right, so there's different kinds of ciphers. There's a substitution cipher. The Caesar cipher is an example of that. There are lots of them out there. Crypto quotes, there used to be these things called newspapers that people got in ancient times, and they would have like a games page, and often there would be encrypted messages there for you to decrypt. Transposition ciphers just moves the letters around without changing them. Rail fence is a classic example of that. The side-tail cipher, which was used by ancient Greece, that was also one example of that. Polyalphabetic ciphers, where you change the substitution alphabet with each letter. So this is kind of interesting, and they're a lot more difficult to break. So here's an example of a substitution cipher that you can work on. This is also on the challenge handout. So if you are getting bored listening to me rattle on, you can work on these instead. Okay. All right. So moving along here. Here's an example of the Vigenere cipher. So this is French, And the example here is Alice and Bob are sending a message, and they have agreed on a key beforehand, A minor. Get the joke, because A minor is a key. Yes, that is my sense of humor, and yeah, you're stuck with that for the rest of the time here. Okay, so the message might be meet me for coffee, and underneath I put the numerical equivalent, right? So starting with 0 for the letter A and 1 for the letter B, going through the whole alphabet, there's numbers underneath each letter. And then we line up the key A minor, and of course A minor is shorter than the message, so you just repeat it as many times as you need to. And then you take the numbers and you add them. So the first letter M added to the first letter of the key A is 12 plus 0, so we get 12. And then the second letter, 4 plus 12 is 16, and 16 is a Q. And in this fashion, you construct the ciphertext. Okay, so there's the ciphertext. And of course, when Eve tries to decrypt that, it's just a bunch of gobbledygook, and it's rather difficult to decrypt. Okay, and then on the other end, when Bob receives the message, he takes the ciphertext, he lines up the keyword that he knows and does the subtraction, and he gets meet me for coffee, and they go to Starbucks for a mocha latte, which is my favorite beverage from Starbucks. All right. You can get hot or cold depending on the weather. Today it's probably cold, right? Because it's warm. All right. Now the deal is that it's very important in the Vigenere cipher for the keyword to be fairly long, because if it's short, you can break the message. You can break the encryption. It uses a technique called index of coincidence and letter frequency techniques. Charles Babbage, back in the 1800s, broke the Vigenere cipher used by the Russians in the Crimean War. And in the American Civil War, the Confederacy used the Vigenere cipher, and the Union was able to routinely break it and figure out where the troops were. So this is something that you need to use it with care. Nowadays, it's not considered secure. It's too old. Computers can break it routinely. However, if you make the key as long as the message, it turns out that this is perfectly secure. Okay, I'm popping over to the Q&A here. Is encrypting hard to do? Ryan's message. Ryan's question. Usually it's done with software. You can do it by hand for some of the systems I've talked about so far, but generally you write a piece of software and it's done very, very quickly. The idea is for it to be fast. How do you get to the challenge handout? I thought that was, yeah, I do not know the answer to that question. Public key infrastructure. We'll talk about public key a little later in the talk. Wouldn't a language be as advanced as cryptography? That only works if no one speaks the language. The Navajo code talkers did that in World War II, and that was a special situation. Yes. All right. I think I've got all of them so far. All right. Very good. Let's get back to the talk. I have to flip tabs. Here we go. All right, so the one-time pad, it turns out that if you pick a keyword that is as long as the message, okay, then it is perfectly secure. It cannot be broken. And it doesn't matter how strong your computers are or how smart you are, it cannot be done. And I'm about to explain why. So here's an example. So we have meet me for coffee. Suppose the keyword is cryptographical. Now that's a word that is as long as the message. And then of course you encrypt it, you get this OVCIF and so forth. All right, now, on the other end, suppose Eve intercepts the ciphertext, but she doesn't know the key. Well, if the key is as long as the message, you can actually get anything. If she were to happen to guess NECGY and so forth that I've written down here and do the subtraction, you get brachiosauruses. Well, that's a real word, right? So Eve might think she broke it, but it's not the right key, and in fact, it's not the message at all. So the problem with the one-time pad is that because the key is as long as the message, there is a key to get any message. And so there's no way to know if you got the right message or not. Just because it makes sense is not enough. It could be anything. And so therefore, the one-time pad is perfectly secure, and it can be always used. Now, of course, the downside is that the key has to be as long as the message. And exchanging the message, well, you have to first exchange the key, and that's not any easier. But nevertheless, the one-time pad is perfectly secure. We're going to circle back to this later. All right. All right, next is machines. Let me check, see if there's any new questions. And I'm not seeing any. All right, moving along. So starting in World War II, back in the 1930s and 40s, they started using machines to do encryption instead of methods that could be done by hand. And here are some examples of some of those machines that were used. And here, you may have heard of the Battle of Midway in World War II. And this was a situation where the United States had broken the Japanese code, and they had used a specific type of attack. So there's 3 levels of attack for a crypto system. One is ciphertext only. So you intercept the ciphertext and you try to decrypt it. And that, of course, is the most difficult thing to do. The next is you may know what the plain text is that goes with the ciphertext, and that may make it easier to figure out the key. In the case of the Vigenere cipher, that completely determines the key for you. But there are systems that are more complicated than that, like the machines that I showed you, where that isn't necessarily true, but it gives you a lot more information. The third and best choice is chosen plain text. In other words, you're trying to break it, and you can get your opponent to use a particular plain text. The United States military faked information about desalination plants on Midway Island, and they were intercepting communications of Japanese submarines, and were able to basically set up a situation that the Japanese would report on, and then they had chosen plain text, and it allowed them to learn the Japanese code word for Midway Island and figure out where the fleet was going to go. And so that was something that they used, and it led to the Battle of Midway. So that's a specific example. In the European War in World War II, of course, the Germans had these U-boats that were sinking the convoys, sending supplies to England, and England needed the supplies to survive because it's basically an island. And Alan Turing, who is also known for being one of the founders of computer science as a discipline in general, he helped the Allies construct machines to break the encryption system. And then the Allies had this interesting problem of knowing all the German messages. But if they used all the information immediately, then the Germans might catch on that their system was broken and change it, which of course would be disastrous. So they had to use just enough information to win the war, but not so much as to make the Germans suspicious and change their system. So that was an interesting little balancing act. That particular secret project was called Ultra during World War II. So that's interesting if you want to learn more about that. All right. I'm checking my time here, moving along. Okay, public key cryptography. So after World War II, a bit, we learned how to do public key cryptography, where the encryption key and the decryption key are different. So then Alice is using a different key from what Bob is using. And public key encryption makes use of a mathematical function that is called one way. It basically means it's easy to compute, but hard to invert or undo. One example of that that's not mathematical is paint. If you have 2 different colors of paint, it's easy to stir them together, but it's really hard to take a bucket of light blue paint and separate the white paint and the blue paint, right? It's one way. That's a one-way function. You do not undo paint mixing. Can't be done easily. So that's the idea. One of the most well-known public key crypto systems is RSA. These are the guys that created that system, Revest, Shamir, and Adelman, and it's based on the one-way function of multiplication. So if I take 2 large prime numbers, say 100 digits each, and I multiply them together to get a 200-digit number, that's fairly easy to do. Now, for a human, not necessarily. That's a lot of work. It's doable, but painful. But for computers, it's trivial, more or less, to do multiplication. However, factoring a 200-digit number into its composite primes, that is really, really hard problem. And that is what RSA is built on. So, right. Okay, let's see. So I'm looking at the time. We're doing okay. Let me see if we have any questions. Right. How can you decrypt complex without the key? Well, that's a challenge, right? That's the whole point, is it's supposed to be hard. It can be done. for certain types of crypto systems. What's the hardest encryption? Well, one-time pad, can't be broken. And what are the major threats to data or information for which it needs cryptography? I don't know if I understand that question. The major threats to which needs cryptography. Yeah, I'm afraid I don't understand your question. Can you ask that in a different way? What do you mean by major threats? Is it threats to the data?
Yeah, I think they're asking what, like, what data or information would you need to encrypt?
Oh, what kind of information? Oh, well, like bank transfers. If two banks are connected over the internet and they want to transfer $1 million from one to the other, that transfer information needs to be encrypted. Otherwise, if you could break that encryption, you could go online and say, oh, transfer $1 million to me, please, and fake out the bank and then get rich. So obviously they need to encrypt that sort of information. So that's the idea. All right. All right, moving along. How's my day? It's going fine. It's going fine. So let me move back to the other tab and we'll keep going. All right. So I'm going to give you a crash course on RSA here. We'll see how we do. It uses a little bit of number theory, which probably you haven't had a chance to study. And but this is the idea here. So Bob is going to generate a key, and it's the encryption key, and he has to keep the decryption key private is the idea. So he chooses two large prime numbers at random, and that's something that we do in fact know how to do. He multiplies them together, and obviously he keeps the prime secret. And he computes this function phi of n. It's just a number, p minus 1 times q minus 1. And then he picks a pair of numbers e and d, so that when e and d are multiplied together, and then you divide them by phi of n, you get a remainder of 1. And this is known how to do. We know how to do this problem. It's not that hard. It's basically based on the Euclidean algorithm for computing greatest common divisors. All right. Anyway, so what happens then? Bob then publishes one of the two numbers of the pair, e, and of course the number n, which is the product of the two primes. But he keeps d private. Well, and he also keeps p and q private. But d in particular is what he needs to do his decryption. Then what Alice does to send a message, she has some message, and we interpret that as a number. How do you do that? Well, if you saw earlier that I had written messages as a sequence of numbers for the Vigenere cipher. If you just glue those numbers together, it makes one large number. And basically, as long as the large number for that message is smaller than the number n, that's the product of the two primes, you can encrypt it and send it. So that's what she does. So she constructs that number, and then she computes m raised to the e power mod n, because she knows e and she knows n from Bob. Right? That was made public information, and M is her message. And what she constructs is C, and she sends C to Bob. So this is all just arithmetic. Okay? Bob gets C, D is secret, and he computes C to the D mod N, which is M, the original that came from Alice. And to recover M from C, which would be breaking RSA, Eve has to compute E, which requires knowing P and Q. So basically, Eve has to factor N into primes. And this is a hard problem. Currently, we know how to factor numbers around 150 or so digits long. Anything beyond that would take multiple years on a supercomputer to do. And so the way around that is just Bob makes sure N is big enough that Eve doesn't have access to enough computing power to break it. And then it's all good. So that's the idea. That's how RSA works. Okay. And that's my next topic. Let's see, do we have any new questions? How did I get interested in cryptography? Well, I've been interested in computer science since I was a kid, and I studied number theory and algorithms in grad school, and cryptography just seemed like a natural extension of that. So it's a lot of fun, I think. So what are my other questions here? Do I have a website with different ways to do encryption? I don't have one myself, but if you Google around a bit, you can certainly find some of those. Let's see, is there one for RSA that's public? I'm not sure, maybe, but all the other ones I've talked about, for sure, you can find websites that will do those. Right. And how do I pick E and D in RSA? Well, you pick one of the two at random, E or D at random, and you compute the other one from the first is what you have to do. And that uses something called the extended Euclidean GCD algorithm, and that will do the job for you. So, all right, I hope that's helpful. And let me move, I'm checking the time here. We got about 15 minutes, a little less. So, all right, I'll just mention Dan here briefly. Well, let's see, I think I'm going to skip over this one. Because I want to talk about quantum computers, because we should talk about that. Okay, so IBM came out recently with a quantum computer that has 127 qubits or quantum bits. They're bits where it can store both 0 and 1 simultaneously in superposition as it computes, allowing it to do massive parallel computations at the same time. Now, 127 bits isn't that many, and this computer is not going to threaten RSA today, but down the road, it's coming. It's coming because this guy, Peter Shor, came up with a quantum algorithm that will factor numbers quickly on a quantum computer if the quantum computer is big enough. And this, in fact, is the circuit diagram of the algorithm to do the computation to factor a number. So this can be done. I think today they factored numbers like 21 on a quantum computer, not really threatening, but you know, once we get large enough quantum computers with thousands of quantum bits on them, it's possible that RSA could be in trouble. So that's a problem. So what do we do about that? We need new encryption systems if we're going to do public key that can't rely on RSA, because RSA will be vulnerable once we get big quantum computers working. So what's the idea? Well, use quantum cryptography. So this is a key exchange protocol. The idea is you exchange bits of a key first, and then after that's done, you use one-time pad to actually send the message, which is perfectly secure. So the idea is to get this key done first, all right? And it uses lasers, so that makes it more fun, right? All right, so we need to know a little quantum mechanics and some physics here. So there's something called the Heisenberg uncertainty principle, which says that when you measure a quantum system, it changes it. And so you can't, measure things or look at things too closely without disturbing the system. And the idea is we're going to fire lasers. So Alice and Bob are going to shoot lasers at each other. They're going to put polarization on the photons to encode information. So they can either use a rectilinear polarization, which would be like a vertical horizontal grid, and based on that you can encode a 1-bit or a 0-bit, or they can use a diagonal polarization. And so a diagonal to the upper right is a 1-bit, diagonal to the lower right is a 0-bit. So that's the idea, is you encode your information as bits in photons and then shoot photons at each other, which is basically a laser, right? That's how you fire photons. So here's an example of the protocol. So what Alice does first is she's going to tell Bob how many photons are coming his direction, so he's ready. Because, when you shoot laser at somebody, they need to know it's coming. So in this example, she's going to just do 16 bits. And then she chooses the bases to use first. So she chooses to go diagonal, rectilinear, and so forth. Okay, that's the top line here. And then these are the bits that represents. She chooses bits for that to represent. And these are just picked at random as well, 0s and 1s, like with a coin flip or whatever. Okay, and then that gives her the polarized photons to send. And she shoots those at Bob. Bob simultaneously is going to pick bases to use to measure the photons. And of course, he may or may not be right. And as he receives the photons, he's going to read the bits that are encoded on those photons in a detector. So like the first one, he chooses the rectilinear, but it was fired with the diagonal, which means he's measuring with the wrong basis, which means that his bit is likely to be inaccurate. He's going to get it right with a 50-50 shot. But when he gets the correct base chosen, when the second position he does that, he's going to get the right bit. So he gets the correct bit. So they go through this protocol and Bob reads the bits. All right, we're not done. So slide number 2. So then Bob tells Alice which bases he used, and it's fine to do this over the internet. And Alice lets him know which ones were correct. And it's okay if this is intercepted. We don't care at this point because it's too late. The protocol's already happened. The laser's already been fired. So once Alice tells Bob which bases were correct, then they know which bits were shared. And these are the bits used as part of their one-time pad. And they just repeat this protocol until they have enough bits to send whatever message they want to send. And then they use one-time pad and they're good to go. Right? So there we are. Now, what does Eve have to do to break the system? Well, Eve has to somehow measure a photon without disturbing it. And that's actually not really possible. So cloning a photon, preserving its state of polarization without disturbing it, and reading it later after she knows the right basis, just can't be done. So the protocol from a quantum physics perspective is unbreakable. So how cool is that? And then they get their one-time pad and they can send any message they want with the shared bits. That's the idea behind this. All right, so let me see if there are some questions. All right, looks like we did pretty well here. I've got 5 minutes left, so if you have any questions for me, what I have here is a couple of references if you want to learn more. I would highly recommend the code book by Simon Singh. It's fun to read, and he talks about the history of cryptography, and he also covers public key cryptography in there as well. And it's designed for a lay audience, as it were. Okay. Wikipedia actually has decent articles on both the Vigenere cipher and on public key cryptography. So you can go there and read more about those. And then these are the references for the actual paper from 1978 that Revest, Shamir, and Adelman published on the RSA crypto system. And then this is the reference for Peter Shor's algorithm for factoring on a quantum computer. The Broussard book, Modern Cryptology, a tutorial, has a good description of the quantum cryptography protocol that I talked about earlier. And there's a reference for Dan Bernstein's case against the Department of Justice, which if we have a minute or two, I can pop back over there and cover that. So I'm not seeing any new questions. So that's what I'll do. I'll pop back over there and we'll look at that. No reason not to. Scroll back up. Here we are. So there's a picture of Dan Bernstein. Okay, so what did he want to do? He invented a hash function, and then he showed how to create a secure public key crypto system based on the hash function, and he wanted to publish this online on a web page. And it was his. It's not like he took someone else's. It was his. And he wanted to post it on the web page. But at the time that this was done, cryptography was considered a munition, like a weapon, okay? And there was a reason for this, but bottom line, it was considered a weapon. And so the US State Department told him he had to shut down his website because he was exporting good cryptography. Now, it's okay to export bad cryptography. We don't care if the rest of the world learns about bad cryptography, but he had good cryptography on his website, and they told him he had to take it down. But Dan didn't believe that this was legal because putting information on a website is protected by free speech in the Constitution. So basically, the Electronic Frontier Foundation supported his case against the US government to sue them for the right to publish his algorithm on a website. And that was the argument, that code and speech are the same thing. And they did sort of win. Okay, so a little more background. Why did the United States government care about this? Well, at the time, the FBI, I think it was the FBI, wanted to have the ability to tap cell phones. And the reason was they wanted to be able to tap cell phones in particular for, say, the mob or organized crime, okay? So this was something very important. So they didn't want cell phones to have strong cryptography on them. The way they prevented cell phone companies like iPhone and all the others, the way they prevented them from using strong cryptography is they passed a law making it illegal to export strong cryptography. And cell phone makers didn't want to make two versions of all their cell phones, one version to use in the United States with strong cryptography and one version with weak cryptography that they could export overseas and sell there. So they would only do one version with the weak cryptography. And therefore, the cell phones have weak cryptography, and then the FBI could tap cell phones for organized crime. So that's how they got this law on the books that made it illegal to export strong cryptography. But it was a pretty broad law, and it applied to not only cell phones, but websites. And even at the time, if you had a textbook that described RSA and you wanted to transport that textbook on a plane with you when you went to, say, travel in Europe, that was considered exporting strong cryptography, which was ironic because at the time this law was in effect, the Soviet Union, which was in existence at the time, was using RSA already. It's not like they didn't know about it. This was not a big secret. People all over the world knew about strong cryptography. So the whole motivation was all about cell phones. Anyway, in the end, Dan won his case against the US government, but I think they still had disclaimers. He couldn't export to Iran and North Korea and a few other places. He was not allowed to export, which is hard to prevent on a website, right? You don't control who visits the website. Anyway, so this is a very interesting case. And if you're curious, I would encourage you to learn more. Dan is a mathematician who does research in cryptography, and he has a bunch of journal publications. You can read about those if you care to. So I'll go back down here, and oops, there we go. So there's a link there to the Electronic Frontier Foundation's website where they describe the case in some detail. You can read like court depositions and all sorts of things there if you're actually curious about that. So, all right, back to some questions. Does quantum cryptography require a quantum computer to use? No, but you need lasers. So that is a downside. What if you use some huge number, more digit numbers with RSA? Yeah. Well, you can't forget the key. If you forget the key, it's useless. You got to remember the key. Making the numbers even bigger makes it more secure, but it also slows down encryption and decryption. That's the thing. If it takes a really long time to encrypt and decrypt, nobody will use it. So there's that. What is the most unique, exciting project that you've been involved with as an expert of cryptography? Well, okay. So my expert is algorithms and number theory, and cryptography just happens to be the main application area. But I have been to many conferences where there are a lot of cryptography experts. What is it? So that lame thing. I know people who know cryptography, but I don't really know it myself. Have I ever had to decipher something for the police or under pressure? No, that is not something I've had to do. No. So that's a good question, though. There is, okay, so there's a place, the government has something called the National Security Agency, and that's one of the things they do. They have supercomputers there and all kinds of stuff, and their job is to do decryption for the government, like the FBI and the CIA and all those folks. That's what they do. So no, they don't go to private citizens to do that sort of thing. They want to be able to keep people under, top secret clearance and that sort of stuff. So what do we have? We've got like 1 minute left. So I have a quick story to tell you. I was at a conference and I knew a person who worked for the equivalent of the NSA in Canada, and then a guy who worked for the NSA in the United States. And we were out having a beer at lunchtime at the conference. And so I asked the two of them, I said, I know you guys can't tell me what you work on because it's top secret, but are you allowed to tell each other? Because the Canada and the United States are allies. And they looked at me and then they said, well, we can't answer that question. So I thought that was hilarious. To me, that seemed like a yes. So anyway, all right. I think I'm out of time. Thank you very much for your attention, and I hope you enjoyed it.